Hello, everyone. Welcome back for another Zephyr Tech Talk. Happy to be back for I think it's our 15th, 16th episode. There's lots of people who signed up and who already started to tune in. I can see. So welcome. As we always do, I think it'd be great to use the next few minutes as we gather people to use the opportunity for everyone to say hi in the chat, whether you're joining us on YouTube or on LinkedIn. Just tell us a bit about who you are, where you're joining us from. It's always funny, interesting to see people joining from literally all over the world and all the continents. I'm Benjamin, by the way, joining from France. I'm the developer advocate for the Zephyr project. And today we're going to be talking about all things tracing and profiling. This is one of those tech talks where I've been working with our guests today, asking them to basically bring hardly any slides. And I think in this case today, there's literally 0 slides, no presentation, more of a discussion and lots of demos to basically dive right in the topic. You're going to all learn, I hope, some cool tips and tricks. And get some pointers to learn more and to experiment by yourself. So with that, I'm not seeing anyone in the chat just yet. So please just chime in already. And I will be bringing our guests for today, who are Anas and Johan. Let's start with a quick round of introductions. Maybe starting with Johan, because I think everyone knows Anas by now. But hey, Johan, welcome.
Thank you. Thanks for having me. So, Johan Kraft, based in Sweden, founder and CTO at Percepio, developing tracing and trace visualization tools, observability solutions for IoT and embedded software.
Okay, nice. And Anas?
Yeah, hi everyone. Anas Nashif from Intel Corporation. Today I am actually reporting from Portland, Oregon in the US, not from Montreal as usual, so I'm traveling. 6 a.m.
Like
my time here.
6 a.m., right? Yeah.
6 a.m. Yeah, but yeah, that's normal time for me. Yeah, so no complaints. And I am actually, I have been involved with tracing since the beginning. I'm actually the maintainer also of the tracing subsystem in Zephyr, among many other things. Yeah, so we'll be happy to give you some history and status of things and where we are. Yeah, that's it.
Yeah, sounds good. And we start seeing people tuning in. I'm seeing lots of new faces, actually. People joining in from Sweden, from the UK, India, France. France represents. We have a few people already. So topic for today is tracing and profiling. And I usually like to say that it's I see it myself as a way to basically understand what goes under the hood, right? When you start using something like Zephyr, which effectively is an RTOS and like provides you with ways to write like several threads and have like synchronization between tasks, etc. Sometimes it starts becoming like complex, and you have either performance issues or a problem that you don't really understand, and that's where tracing and profiling starts kicking in, right? So like, Anas, do you want to tell us a bit more maybe about how you see things and like what we're going to see today in terms of demos and
So you are correct. I mean, there is different. I mean, this is obviously like a topic that it's a tool for debugging, right? This is not something that you run in production, and so you probably can. I mean, there are probably use cases, to detect anomalies and stuff like that. Yeah, probably Johan can talk about this from his perspective. But I mean, looking at Zephyr, I mean, the way things started when Zephyr was started, only thing we had was print K. Yeah, so basically, as a lot of engineers like to do debugging, you just go and start adding print Ks all over the place and get some output and figure out what is going on. Obviously, this does not scale, and you especially with a real time OS where you actually a lot of things happening like so fast, context switching, and so on. And Brent K will come and be in the middle of all of that and probably disturb what you are trying to debug. And then the next level of things, obviously, that comes when it comes to debugging is like, you can actually connect a GDB and look exactly what's happening there. And that, like, very early on in Zephyr, we added OS awareness, like, for GDB, so you could actually see, like, look at what threads are running and so on. But still, this was not enough. Obviously, you have also logging, like deferred logging and so on. Yeah, so that came a little bit later, and at least in a more advanced fashion. I mean, we had like very early logging that is basically was based on Brink-K, but then we added like deferred logging, and then you actually it was also module aware, or you were logging based on what subsystems or components of the OS you are interested in. So a lot of cool stuff that we added, but still, logging was not enough. Logging is just, tells you, hey, something happened, like whether it's an informational, whether it's a warning, whether it's an error, etc. But it does not give you an idea about what the system is doing as a whole, and you can actually be overwhelmed with many log messages. And at some point, probably if you add logging in the core of the kernel, and when you are context switching and so on, that just doesn't work. I mean, you will be overwhelmed.
And same for debugging. You don't want to like sort of put breakpoints everywhere and basically change the behavior of the system that you're actually trying to debug.
Exactly, and that's where we started adding tracing, and there are different ways to do tracing, and it also depends on what you understand on the tracing. I mean, there is lots of tools available to you, like from the toolchain, from the compiler, so you can do like instrumentation. You can add like hooks into each each function that is executed, and then you can go and look at like some type of heat map. No, not heat map, like, so you can see exactly what is being executed and so on. But it becomes overwhelming, because if you are trying to figure out like some synchronization problems that your application has, like you have a couple of semaphores, a couple of mutexes, like you have something with data communication, a couple of threads, different priorities that are switching between each other. It becomes very difficult because there are so many functions that contribute to all of this, and you don't want to be looking at each function, sometimes internal, to identify a problem. And that's really where tracing comes. Tracing is really, at least in Zephyr, the way it's done is it's context aware. So it's context aware. That means when you add a tracing point, you know exactly, or you tell you want to use these tracing points to know exactly when you entered something, what are you doing exactly, what is the data that you are passing around, and when you are done with this. Obviously, you want to measure the time and show that in a way that the developer, or whoever is debugging the system, know exactly what's happening there. And there are many ways to do that. We started, actually, it was very bare bones, it was very simple. And initially we added like CTF, which is the common tracing format. We used the same infrastructure to enable system view, but that was also very limited, and it was like there was a lot of hard coding, and then basically we started talking with Johan and his team, and based on the experience they have in this area, we actually reworked and overhauled the complete tracing system, and how we add tracing points, and I will be showing that in a bit, and how to make it also application or tracing application agnostic. So it doesn't really matter if you are doing something on the command line, as I will be showing, or using a tool like Tracealyzer from Percepio, or even using like other tools. There are so many other tools out there. I need to mention here that we also support System View from Zagar as well. I wanted to show something, but it's somehow I forgot like the probe, which would help me do that. Yeah, so I will just be showing things on an emulator. The other nice thing about tracing is that contrary to other tools, like instrumentation or profiling, using like in the kernel directly, is that you can do that real time. Yeah, so you can actually be connected to a device and looking at the screen and seeing exactly what's happening. Yeah, because you are streaming the data and the application processes that. And I think Johan will be talking about that. Contrary to, hey, I run an application, I dump data, and then start looking at the output. Yeah. So it's actually, you can be interacting with the system. You can be pushing buttons or doing, or like getting like network events and stuff like that, and see exactly what's happening on the screen, which is really great for debugging, because you can do a lot of things there. So yeah, without, further ado, I can actually start sharing, showing you like, need to look at the time here. Yeah, we are, okay, let me look at the time. I don't want to, so my demo is actually very simple. You can you see my screen now?
Yep.
Okay, so, oops. I'm showing the end result, but that should be okay.
Yeah, that's why I was waiting to share your screen. I was waiting for you to clear it.
Sorry. So yeah, because I am on a laptop here, and it's
only one screen. Yeah.
Yeah. So basically, before I go into that, just going back to what I have said. So looking actually at the kernel, for example. Yeah. Clear. Sorry. So let's just take an example like threads, right? This is like where threads are implemented, and this happens to be, well, thread probably is actually a bad example because there's a lot of things going on. Let's take semaphores, yeah? So semaphores, like let's go KSM init, this here. And this is where the implementation of, when you initialize a semaphore. So it's like the code you have here, error checking, etc. But then you see this guy here, sysport tracing object function. And this is like a general macro available, where you define basically the object, the primitive you are tracing, the action. In this case, I'm initializing, and then also some parameters, right? So this is basically something that can be implemented depending on the application you are using for tracing. So this is like the init part. And then you have somewhere here, I don't know where it is. Yeah. So there is no end to that, but let me go to take. So here you have enter. So this was like a function that is like instant, I would call it. Yeah. But here you have something where you enter and you exit. So you can actually see when, because there's some timeouts usually and delays and so on. So you want to see basically on your timeline, basically when you have entered the take action and when you actually exited that. And that's something you will see in the tracing, either on text format or in a graphic way. Yeah. So, and that's basically how things are implemented. And these macros, depending on the implementation, would be implemented in different ways. Yeah. So basically, that's the last thing before I switch to running that. Oops. So here, for example, using CTF, for example, all of these macros that you see basically in the code directly would actually translate, by a few levels of redirection into something like that. In CTF, in the CTF case, this is basically the semaphore init, and that would generate a CTF event. We know it's a semaphore event with the semaphore ID and the return code. Yeah, and that would, in the case here of CTF, that would end up, as a a binary format that is you can save and push over serial, or you can just write into a file and then decode using some open source tracing tools.
Yeah,
So,
and I guess whichever backend is going to be used, whether it's CTF or something else, is something that I just configure when I build my
yes.
app. I guess
Yes.
this is like
Yeah,
just
I will
updating
show you
it,
that.
right?
Yeah. So I took the philosopher sample that we have in the tree, and basically what I did here is just removed whatever was there because it was completely irrelevant. There were like two, configuration options which were not really important in this case. I just removed them. Yeah, and I enabled tracing. That's where I actually pick CTF, and Johan probably for Tracealyzer will pick something else. Yeah, and then I define the backend and also the tracing size. Yeah, so the buffer size, and that's like we have a buffer. You can also do direct. I mean, depending on your backend, because that's like really the interesting part, which is worth mentioning. You are not always writing into buffers or sending data over some channel that is deferred or something like that. You could actually, your tracing macros, like in the case of say Zephyr and like a lot of like ARM microcontrollers, you actually have like you have interfaces to send tracing events with very low overhead. So you, without interrupts and without, like, you don't have to go over UART to do that and add some overhead to your tracing process. So you can actually be writing directly to memory somewhere, and which is then, on the other side, on the host side, you can just read them without interfering too much with how the application works. So that's basically what you do here, depending on your application. The size here might vary and so on. And the other addition that I did is here, beside like the configuration, is that I want, at least in the case of Chemo, I am adding this here, which writes the serial output into a file. I call it channel 00. Yeah. And beside that, I don't have to do anything else. So I just actually go, build the regular way with Wisp build, and the application runs. A lot of things happened. I mean, it's just a few seconds, but here a lot of things happened. And that actually will give me, if you look at the build directory, you give me this channel thing. And if I, just for fun, if I open that, this is binary stuff. This is like the CTF format, and you will start seeing like tracing thread and stuff, like, so things that will be displayed, or philosopher. These are like the thread names and so on. Obviously, this is not really what you want to look at. Yeah, that's a lot of garbage. That's where you actually can, so for CTF, we have also like a metadata. We need to tell the tracing application how to interpret this data. So we have in the tree like the metadata for CTF, subsys, tracing, CTF, TSDL.
Oh, so it's not application specific. Like it's really just like once and for all. Okay.
Exactly. So this is like the metadata. That's what like a tracing analyzer would look at.
Yeah.
Exactly. Yeah. So it tells you exactly, basically, this is all of the things that you have there, and that is something like the application would need to, or the tracing, the tooling needs to analyze. So basically, what I do here is I copy the build channel into a directory, but then I also have to have the metadata. I just copied that earlier. So the metadata I have there, and then using some, on Linux, Babel Trace. This is like an open source tool that can deal with this, and I just do trace, and you get all of this output. Now, that's obviously, I mean, there are tools which can actually take CTF and visualize that. Trace
Compass, right? Yeah.
Yeah, for example, yeah. There are like also the Google tracing tool that is implemented in Chrome can deal with that as well. You can convert that in JSON, and there are so many ways. But right now, in Zephyr at least, we just provide this, and it shows you basically exactly. I mean, the whole idea here is that you have all of this is like happening in microsecond scale, yeah, and you have the timestamp here, and you can basically see, I'm unlocking mutex. There is a thread that is switched out, the philosopher 2. I go into idle, and so on and so on. And here I am in the idle thread. I have an interrupt. This is probably the timer. A semaphore is being entered. Semaphore exited immediately, probably, and so on. And it goes all the way. Obviously, this is unless, I mean, you really have to be very close to your application to know what's going on here, and know exactly where to look to see anomalies or something that took a little bit longer, and so on. And that's where a visualization tool will be really appreciated, and that's what Johan will be showing with Tracealyzer. So unless there are any questions, because I didn't see any questions on the screen while I was sharing.
Yeah, no questions so far, but yeah, I encourage everyone to start lining them up and not wait until the very end to ask them. Yeah, it would be great, I guess, to switch over to Johan to get more, even more tooling stuff.
Yeah, thank you. Yeah, I can only agree with the background that Anas gave. I mean, there is a fundamental difference with, I mean, if you compare modern RTOS development with Zephyr, with a kind of old school embedded development with a super loop, you have a whole new layer in between the multi-threading, and that can bring a lot of pitfalls, and you're not in full control of the code. It's not as explicit, at least. The source code that you're looking at is not always the whole picture, so to say. So with Tracealyzer, you can get the runtime perspective, and that is quite useful for many things, not only profiling and trace debugging, but also you can review the software design and things like that. So I believe I'm sharing.
You are, yes.
Yes. So I have here the corresponding setup, the same example, the philosopher's problem example. I mean, this is a classic computer science example where you have 5 or 6 philosophers that are sitting at a table, and they're sharing resources, forks, and they need 2 forks to eat. And they can be in different states. They can be thinking, they can be eating, and they can be etc. And the question is if it's possible to make everyone happy, so all gets to eat, or if there will be a deadlock where no progress can be made. So I've made a setup here with the Percepio trace recorder, which is available in the Zephyr tree. So in the same way as with CTF, we enable tracing. I also need to enable the semi-host setting here for this particular. I'm running on the QEMU Cortex M3 board simulator, and the data is the tracing backend here is semi-hosting in QEMU, so I'm actually writing the data directly to a host file on my computer, but we also support other ways to get the data out with Zephyr RTT and other ways. You can also use network connections and things. We enable the Percepio trace recorder and the start mode, that is basically if the tracing is to start immediately that we want here, or if we want to start it by interactively from the tool. And then I've also enabled the Zephyr semi-host stream port. A stream port is a Tracealyzer concept, which is basically a header file that defines how the trace is written. We have 7 or 8, 9 different stream ports available in our repository, including ITM, Zephyr RTT, TCP, UDP, other versions, and it's quite easy to add your own if you like.
And this works with Zephyr upstream, right? Like the trace recorder module is available as part of the official Zephyr manifest, right?
They're found under modules Percepio.
Right.
So with this, we can run the example. This is as mentioned, the same philosopher's example, although I've added some additional code just to show some additional Tracealyzer features. Not required though. We could also use the plain philosopher's demo. There's a pop-up from Tracealyzer in the background. It noted that the currently open trace had been removed during the build. And the trace file is stored in the build folder in this case. So now it's including the trace recorder and it's running the trace, and this is generating a fair amount of data, so I better stop this in time. Like that. And we can switch over to Tracealyzer. And here we see I'm running this actually in WSL on top of Windows right now. So I'm using the Linux version on top of Windows for some reason. I found that the disk performance between Windows and the Linux subsystem was a bit slow, so it was easier to run this on the Linux side. Right, let's hide a few things so I can explain what you see here. Like that. So this is the same system, the same trace basically as Anas showed, but here in visual form in Tracealyzer. This is a tool we have been improving over more than 10 years actually, and it has a lot of different views to show different things, and it's been kind of optimized for RTOS based systems. We've also added Linux tracing support. Most people react initially that the trace view is vertical by default. If you like, you can change that and have a horizontal view. But there is a point with the vertical view. Some people feels that this is a natural way, just like you scroll a text file or other document. And it also makes it possible to show annotations as textual labels in an easy way. For example, we can see mutex events like this. So here we can see how the different threads, the philosophers, and also the main thread here are well, first we create some mutexes and threads, and then we can see how they are interacting. We can zoom out a bit to get more overview. So we have different colors here to indicate blocking and resume from blocking and so on. Tracealyzer has a fair amount of intelligence, so to say. It understands what events that are related. So if I click on, for example, the event here, it highlights the related events. That is the point where the blocking began, and here it ends. If we zoom in a bit here on for example, this execution, we see these solid rectangles they indicate actual execution from when the thread is switched in until it's switched out. And then this shaded area here is time when the thread is still active. It's waiting for something typically, but it's not actively running. In this case, we can see that the thread is blocked by a k-mutex lock operation. The mutex wasn't available. And we see that it's unlocked here, I think. Yeah, at some point it's unlocked and it resumes. It's actually possible to see the point where it's unlocked by, I think it's that one. Yeah, that one. So that shows the connection between kind of the causal relationship, the cause and effect. The unlock is called here, and that results in this operation returning. It's also possible to see. I think this trace view is it's often quite useful for debugging things where you have synchronization or scheduling or timing problems. You can see in quite a lot of details what's going on. Now this is a simulated QEMU environment, but we can see that the time scale here this is in microseconds, so that's 13 milliseconds there. But Tracealyzer also has a lot of profiling functions. And these profiling features are based on the trace data, so it's not sampling, but it's kind of exact, although the instrumentation overhead can have a small impact, of course. So, for example, if I click...
Do you have a sense, by the way, of, I guess the short answer is it depends, but like what's the typical overhead that you're...
Get that question a lot. Yeah, I mean, it depends on the processor speed and the amount of instrumentation points, and of course, how efficient the trace recorder is implemented. It depends on the compiler optimizations, etc. But it's rarely a problem, I would say. If you are doing real-time computing in the milliseconds domain on something like a 32-bit Cortex-M or larger, then it's typically no problem. We have seen issues in some cases where people have very tight real-time loops where every microsecond matter. If you're doing say a communication protocol that is doing software bit banging or something like that, then it can be an issue sometimes. But it's rarely that we get any feedback about that. Yeah, we have a lot of different views in Tracealyzer depending on how you count. I think it's over 30. I think there are 7 or 8 different types of visualizations, and then there are many different data sets that can be displayed. And the idea is to, I mean, you can of course just look at the raw event data, so to say. We can open the event log and see all the details. But yeah, we have hundreds of thousands of events here, 200,000 events. I have some issue with, it seems that running Tracealyzer in WSL on top of Windows is causing some font issues. But, and of course you can search for things here if you like. You can type in a few letters and identify things.
Yeah, and there's a question from Christopher, and I think it's actually showing in the UI. We can see that for the threads, for example, we see the addresses. It does support things like the names as well, right? Like it's getting metadata from the Zephyr objects, right?
Yeah,
it's there on the top. Yeah, you can see that.
The vertical
with thread names here, and Tracealyzer can show names for all sorts of objects. Maybe this demo isn't.
And like maybe things like thread priorities or like the kind of metadata captured and associated to kernel objects, I guess you're able to surface, right?
Yeah. I mean, in general, the way it works is that the trace recorder needs this information. And typically we capture information about names and things like that when by instrumenting the create calls.
Yes,
so,
stack size we can see right there. Yeah.
Yeah. Right, but what I was coming at was that you can, if you know what you're looking for, if you want to inspect a certain sequence, you can type in something like, let's say, starving. Do we have something like that? And find such events and find them in a trace like this. You simply double click here and find them. But in some cases, maybe you see an issue in system testing or so, where you only have some kind of abstract symptoms that something was running slow or something. You don't really know what you're looking for. And then it's good to have higher level visual overviews where you can spot anomalies and then drill down on those locations. So Tracealyzer has been designed for this kind of top-down workflow where you can detect or spot visually potential explanations for issues you have seen and or anomalies in the execution, and then double click on that and drill down into the details. And we have a lot of different views like that. For example, this view here in the lower right corner shows a summary of the thread executions with respect to different time metrics. So here the timeline is actually horizontal, and each of these points here represent one execution of a thread like this. And the y-axis here shows the execution time. So this way we can see the variations over time. So for example, we can see that initially we have some quite long executions up here, but then they are shorter. And we can also look at other metrics. Execution time is the actual CPU time used by the thread, but if the thread is preempted or blocked, then it will take longer to complete. And then you can look at response time, which is the full wall clock time, so to say, from the beginning to the end of the instance. So here we can see some extreme examples where we have very long response times because other threads are running or because the thread is blocked by, for example, a mutex. So here this poor philosopher needs to wait a long time to get his fork. Most views in Tracealyzer, if not all, are interconnected in this way. So you can click on something and locate that in the trace view. In the same way here, the CPU load graph, you can click on a peak like this and see what part of the trace that was. The CPU load graph shows you basically, it's a histogram that divides the trace into a number of small sections, and then it counts the CPU time for each thread within those buckets, so to say. So this is useful both for profiling to get a sense for the overall load, but it can also be a navigation tool to find interesting points in the trace. As you see, the scale adjusts a bit. Here we have a peak at over 50% load, and then when I scroll past that, it adjusts, so we're about 10-15%.
It actually does give us a sense of the overhead of the tracing, does it not? Like, what is TZ control in this case? Like,
that is actually right. That is actually part of the trace recorder. Yeah. In this case, I think what it's doing is that it's doing stack monitoring. You can configure that.
Right. So it's pretty aggressively monitoring, maybe.
Yeah, that is a kind of expensive thing. It basically periodically checks the available stack or the stack remaining of the threads, and that is configurable. We can have a look at that and see how much that takes. So in this case, that loads with about 3 or 4%. So that's a bit much, but it can be. We can see the result here in the stack.
I think this thread is created like also with the lowest priority available. I mean, so
Yeah.
it does not interfere with the
Yeah,
application.
it's not. Yeah,
It's running a low priority. In some, depending on what backend you're using for the tracing. For example, if you're tracing over a TCP connection, then we also need this task to do the actual kind of data shuffling. We have so many.
Stack usage, yeah, right there.
There
you go.
So here we can see that the. Let's enable those. So we can see here all the we have a lot of sample points here, so this is very excessive. The idea is that with this you can see where in the trace that the stack usage is as lowest, basically where you find the deepest call chain, and then but there are other ways to analyze worst case stack usage. But this can be configured in kconfig, so you can disable it altogether if you like. Otherwise, I would say, I mean, as mentioned, the low CPU overhead of tracing depends on many things, but if you're running this on real hardware with something like J-Link RTT as backend on, say, a 200 megahertz Cortex M4, you're probably looking at an overhead of 1 or 2%, depending on the amount of events, but it's in that range. It takes some microsecond to log an event, and you're typically logging a few thousand events per second. Right. Just double check my notes here. Yeah, so I mean, there are different use cases for this. As mentioned, trace debugging. If you don't have observability like this, it can be really difficult to debug certain type of multi-threading problems if you're not quite sure where to look. I mean, with multi-threading, the connection between it's not always apparent from the source code how the execution will be. So you really need to measure that in runtime. I mean, you have things like preemptions and blocking and variations in execution time that affects that. So the order of events can vary depending on many factors, and that can of course affect things like bugs and performance issues. We've heard from customers that they've actually managed to reduce debugging time by something like 90% by having a tool like Tracealyzer, or actually Tracealyzer in this case. Another use case is profiling and optimization, of course. Not only on thread level, you can do more advanced profiling and set up kind of checkpoints and measure the time between point A and point B in the code and get statistics on that. And the important thing is not only that you get the metrics, but you can also see why. If you have a very long latency, for example, at some point, you can see in the trace why that was and understand, fix the problem. We had a customer in the US that were developing welding equipment. I think they were running FreeRTOS, actually. This was many years ago, but the multi-threading issues are similar. And they found some, when using Tracealyzer, they could find some issue that when they solved this quickly, they reduced the CPU load, the processor load by basically 3 times, from 45% load to 15% load. And even though they were not using the full potential of the processor, it means that they can potentially run the system on a cheaper, more cost-effective processor, or avoid hardware upgrades in the future, or also make the system more responsive and allow for adding more code, more features. I mean, debugging is of course a common use case. I would say that's the most common case among our customers. We often get in touch with developers when they have a problem and they are interested in using Tracealyzer to see if that could fix it or get them the observability they need to understand the problem. And that's but once they have seen what Tracealyzer can show from their system, they tend to use it more and more, and often use it quite systematically. So it's not only like a fire extinguisher for solving the really difficult problems, but it can actually be like a debug console on steroids, so to say. And we have quite a few customers that use it basically on an everyday basis, and they have made quite substantial gains in productivity. We have one case in the Netherlands, for example, a company called Flyability. They have stated that they have doubled their development speed by having Tracealyzer in their process, so to say. So they can
maybe you can actually show it. I think you have a short demo of, because like what we see right now is more like sort of the built-in traces, right?
Yeah.
In like the kernel itself. But I guess as an application developer, if I'm writing my own threads with my own like business logic, I might introduce some bugs and deadlocks there. And there's a way to visualize that as well, right? Like the actual stuff that whatever the dining philosophers are doing, we could also sort of visualize and materialize here, right?
Yes.
Like what state they're in, or
I'm just getting started here. So what we see now is basically the kind of kernel events that you get more or less automatically from Zephyr when enabling the tracing. But you can also add additional instrumentation in your code to get more information. For example, let me switch to the code and show you. So I have the main function of the philosopher's example here. I've added some things. If we start with this call, so this is like a printk or printf basically, but it goes into the trace. The first argument here is a channel. That's just a way to group these messages so it's easier to follow. So we're logging the time this philosopher is allowed to eat here. So we can see this in Tracealyzer by enabling this in the user event channels. So this is data we already have recorded, but I have hidden it initially. So if we enable these, we can enable all. We see them in the trace like this, and this parameter here, the time the philosopher was allowed to eat, can be seen here in this data plot. So if let's select unsynchronized filter, then we can look at these different channels, these different philosophers, and this kind of user events can be used for anything really, not only dining philosophers, but it can be a variable in your code of any kind, or some register you want to log. It's a general logging feature, but it's shown within the trace, and that way you get more context around the logging. You see from what thread it is. Well, that you can get anyway, but you see what the threads were doing and what other threads that were running, the scheduling and things like that. So this is a basic form of, let's call it application-specific tracing. So I only needed to add 1 or 2 lines of code to get this. And these philosophers also have a state. They are either eating or thinking or waiting for a fork or things like that. And of course, embedded applications also have a lot of states. It can be hardware states or software states. In a similar way, I've added this in the code, some tracing. We have this. I've added all the trace codes are mine. The other code is existing demo. So I've added codes like this to log these state transitions. And
could this go in a CTF trace as well? Obviously, then one would need an actual tool to make sense out of the information. But is this something that could be done? And maybe this is a question for Anas. I don't know. But
No, that's like very Tracealyzer specific. But there is actually something I have been thinking about for a while, is allowing also for user type of defined traces. In Linux, actually, you can do that using CTF. That's probably something we need to look at. But this is, I mean, right now, as you can see, you are using like Tracealyzer APIs, something that is defined probably in the module using a custom header. Yeah. We could definitely abstract it in a way. I don't know. Yeah. And then make it work with others. But no, right. This actually just works with Tracealyzer.
Anyway, so I've initialized the state machine in the beginning here. So I've defined the names for the states, and I receive handles for these. And then I just refer to these handles in the state transitions. You could, of course, implement this using an array of handles instead, and using the state variable to index that array. But this was more pedagogical. More easier to follow, perhaps. So yeah, in Tracealyzer we can see this by enabling the interval sets here. So now we get the state of each philosopher shown in parallel with the thread scheduling. And as you see, this gets a bit messy. We can expand the view a bit.
So you said there's always two philosophers dining at the same time. So that's what blue is. Blue dining?
No, there are 6 philosophers, and each of the colors here in the swim lanes are the different states. So we can expand this to see more information.
Oh yeah, the columns are the states. Yeah.
Right. So like this. And if we're interested in okay, so what's the longest time a philosopher is starving? We can just double click on that, and we can see some statistics here and find the longest here. So 630 milliseconds here for this case. And if you don't want to see all the ones, you can of course change the filter to just show one at a time. And if you're interested in seeing what how the state transitions look like, you can actually see that in the state machine graph. So this is generated from the trace events. And so basically, as you saw in the code, we have the initial state is starving, and then it wants to get one fork, and then it gets another fork, and then the philosopher can start eating. And then it drops one fork, or drops the forks, and thinks for a while. In this case, all the state machines are the same. But we can also generate this for a particular section of the trace, like this. Yeah, the font issue on WSL here. Okay, too big. Let's take a shorter one. So now we only see a part of the states here. A similar view we can generate in Tracealyzer is what we call a communication flow graph. It shows basically the runtime dependencies, what threads that are using what objects. So in this case, we see the philosopher threads, and let's hide that one. And the mutexes here that represents the forks. Not sure why the names are not showing, but maybe I just forgot to set. I think you need to use a specific API function in Trace Recorder to assign names to things like mutexes. If you want to
Yeah,
see.
I mean, mutexes are not named in Zephyr. Yeah, but yeah.
In general, we can name things using the Trace Recorder API. But
okay. Yeah.
I didn't think about that. So here we can see the kind of relationships. This means that Philosopher 4 is accessing this mutex and that mutex, etc. And we can actually click on these to see the corresponding events like this.
That's a lot of data, yeah. Whenever you look at that, yeah, this is. But I mean, just to remind everyone here, we are not like a World Food Program trying to feed philosophers. This is actually, all of these concepts can apply to most complex application, network, Bluetooth, you name it. I mean, that's just transpose that into how your application works and so on, and that actually would show you. Yeah, so it's really amazing. Yeah.
Yeah, you can do a lot of things with tracing, and especially if you combine this with visualization that makes this data kind of understandable. So this is an area I'm very interested in, as you understand, and we have.
That's really cool. So for some reason, people have been really quiet in the chat, and we didn't get many questions. But I guess that's a segue into reminding everyone, if you're watching us from LinkedIn, you might want also to follow our YouTube channel and subscribe to the YouTube channel, and post questions. Like, even if you're watching the recording and you're just catching up, ask a question, and we will make sure to answer it offline, I guess. One question that I didn't see in the chat, but I have myself for Johan, is how does one get Tracealyzer? Like, is this a commercial tool? Is this, like, how does one get it?
Yeah, it's essentially it's a commercial tool. The Trace Recorder is provided open source to make it easier to integrate. But yeah, we make a living from these licenses. Sure. And Tracealyzer is offered as a subscription, and you find it at percepio.com. You can sign up for a free evaluation and download it right away. And we have instructions for Zephyr on the getting started section. I noted that the instructions for running with QEMU was incomplete, or there weren't any specific instructions for QEMU, so I'll make sure to add that, so to make it easier to try.
Yeah, that'd be great. Before we wrap up, I mean, we might have time for a couple more questions if they come like now. But there is a question that I guess you two can you can give it a try. It's tricky. I see an explosion of data that's really useful, but which is the most helpful data if I have to pick just one?
Yeah, difficult to say. It depends on the case. If you're interested in profiling, for example, and you want to get a high-level overview of what threads that are using how much resources, you can have, for example, have a look in the statistics report and get this high-level overview. And here you can see, for example, the response times and execution times. And then if we have a case where we have an anomaly, we can just click on that point.
Yeah, you start with the summary, and then you look at the
so you're kind of starting at the top with the most abstract data, and then you're using that to identify things that stick out, and then you drill down. And of course, the trace view is central. That shows you it's also an abstraction, of course. The most detailed raw view, so to say, is the event log, but that tends to be kind of overwhelming, even though you can filter it in many ways. For trace debugging, it's often useful to use a combination of the trace view with custom user events. You can insert your own events in the code to highlight parts, log variables, and have debug messages. Scheduling perspective is perhaps a bit abstract in some cases, and you need more information. And the way you solve that is by adding what we call user events, like like this one, for example. So in a way, this, I mean, conceptually, this is not very far from printf logging, but there are two differences, two important things. One is that this is deferred, and all the string formatting is in the host tool, so it's fairly quick. It's not like a print K. And also with the visualization, you get a much better understanding of the context and the situation where the system was in. Yeah, so it's hard. We usually recommend people to get the sign up for the evaluation and try it yourself. There is this there is a Zephyr demo included, a trace like this. Actually, the old version at the moment, not the states here. But I'll also share the setup for this case.
Okay. There's one last question, since I'm actually interested in the answer. Let's take it. I know we are slightly over time, a couple minutes, but Aaron is asking whether the tracing framework, and I guess it's like at the Zephyr level, not necessarily Tracealyzer, does it support ARM core site for ARM and ntrace on RISC-V?
I mean, we support, for example, SWO and ITM based tracing on ARM Cortex-M devices, and it's fairly easy to set up other integrations, since you can define your own header file with how to output the data. Core site includes different interfaces that can be used for instrumentation-based trace that we're using. We also have actually some prototypes that utilize hardware-based trace data, but that's not what we're using in the public products at the moment.
Okay. Well, with that, I think it's a wrap. And yeah, I mean, Victor was commenting on the fact that maybe the fact that maybe we didn't get so many questions is because it's like pretty hardcore to some extent, and people are just digesting all the data and all the information. We will be back in a few weeks for another Tech Talk. I think I shared the links throughout the stream. If you were watching this and are interested in coming on the show to present something cool, doesn't have to be crazy Zephyr specific, as long as we're covering some cool embedded topics. I'm fine with that. So please just ping me. And yeah, thanks so much to you both, Johan and Anas.
Thank you.
If you have some links to like code, etc., you want me to make available to the viewers, I will make sure to add them to the description of the video. And yeah, we'll be back in a few weeks.
Thank
Bye.
you.
Great. Thank you. Bye.